and welcome to today's webinar on the European Space Agency's EOPF Sentinel Zarr Sample Service. We are delighted to have you join us today. This is the fourth webinar in our new series designed to help a wide range of users explore and adopt the new EOPF Zarr data format. My name is Dimitri, and I'm a contractor to the European Space Agency in the consortium which is implementing the EOPF Zarr Sample Service, a team of Earth observation, satellite data, and IT experts. The service aims to offer easy access to Copernicus Sentinel data in a cloud-friendly open format, making working with EO data simpler, faster, and more flexible. Today, we will showcase the xcube EOPF Data Store and demonstrate how to create 3D data cubes from multiple EOPF Zarr products. Before we start the webinar, just a few things I'd like to point out. The session is being recorded and will be made available afterward on the EOPF Sentinel Zarr Samples website. And in terms of Q&A, we ask that you use Slido for any questions. Not the inbuilt Q&A function, but Slido. Also, the chat function is not available, but Slido session will be open throughout the whole of this webinar. And we will address the questions asked there during the Q&A session. And if we don't get to answer questions during that session, we will update the Q&A after the webinar and publish that on our website. There's also our community support page where you can post questions on this webinar or any other topic related to this subject. We have a number of resources available to you on our website. So if you access the website, you will find the webinar recordings, Jupyter notebooks, and our open source plugins library under the knowledge and tools section of the website. And this is a link to our community support platform on Discourse. So now I'd like to introduce with great pleasure our speaker for today. Konstantin Dokas is a software engineer with a strong background in remote sensing, scientific computing, and mathematics, with a focus on geoscience applications. He holds a master's degree in scientific computing and a PhD in atmospheric physics, specializing in spaceborne remote sensing. Proficient in Python and modern software engineering practices, Konstantin applies his expertise in geoscientific data to build innovative solutions for efficiently processing and analyzing large volumes of Earth observation data. With those credentials in mind, he is the perfect person to introduce today's topic. So, Konstantin, it's a great pleasure to give you the floor.
Thank you. I need to get the permission to share my screen.
Okay. I think we have addressed that.
Okay, yes, I guess this works. Okay, so first I would like to start with our notebook gallery, which you see over here. Over here, we publish all our examples within this project. And we restructured this gallery a little bit by grouping different notebooks. So we have a Sentinel data category, an application topics category, and a tools libraries category. And today I'm going to present you the new xcube EOPF Data Store, where I also published a notebook just, one sec. Just before for this webinar. To run these notebooks, you can use our Jupyter Hub. You just click on this link and you use your CDSE credentials, log on, and then you can use our Jupyter Hub. Just follow these instructions. Regarding the repository, this is in our GitHub organization. So the code is fully open source. You will find it in xcube EOPF. And we also published a documentation to that package where you get an overview and also a more extensive user guide. But yeah, this extensive user guide basically covers what I'm going to show today in this webinar. So let's get started with this webinar. Today I'm going to introduce the xcube EOPF Data Store. And first I will give you a small introduction, show you how to install this package, Then I will give you an introduction into Xcube in general, because this data store is a plugin for the Xcube ecosystem. And then I will focus on the main features of that Xcube EOPF data store. And then we will bring the theory learned into action. So I import the modules which we need. We go through the functionalities, like the basic functionalities of a data store in Xcube. And then we will open up multiple Sentinel-2 samples represented in an analysis-ready 3D data cube. As a last point, I show you an end-to-end example. This will be a large example where we use this newly developed plugin as a data access. We persist this data cube and save it, and then we can use the built-in visualization tool in Xcube to explore the data. And then we will conclude. Okay, so as an introduction, the Xcube EOPF is a Python package. And as said, it's a plugin to Xcube, and it adds a data store with the data ID EOPF-Zarr. We use this data ID because it's the same engine ID which we use in the xarray backend shown in the webinar 3. And yeah, this data store can be used to build 3D analysis-ready data cubes from multiple EOPF Sentinel Zarr products. I've shown you the GitHub. We encourage the user to use that software, try it out, and write a lot of issues such we can implement that in the next development cycle. And I've also shown you the documentation. Here are the links again, which you will find in this notebook. And the main objectives basically today are how to use this plugin to open multiple EOPF Sentinel-2 Zarr samples. And you should understand at the end the key features and the capabilities of the data store. To install the Xcube EOPF data store, we published that package on pip and on conda. So you can either use pip install or conda install. If you use Mamba, you can of course also use Mamba install. As a general introduction to Xcube. So Xcube is an open source Python toolkit, and it is built for transforming Earth observation data into analysis-ready data cubes. It enables efficient data access, processing, publication, and interactive exploration. And these are basically the 4 key pillars of Xcube. So you have Xcube data stores for the efficient data access, then some functionalities to process that data, manipulate it into analysis-ready data cube. Then we have an Xcube server, which is a RESTful API to publish and disseminate these data cubes. And the Xcube viewer is the counterpart and communicates with the server, which is a web-based visualization application in the end, which we're going to see at the end of this webinar. To focus on to data store, because in this project, we built a new data store for the new Sentinel Zarr samples. So data stores are implemented as plugins. And once they are installed into Xcube ecosystem, it registers automatically. And then we can use this new data store method in Xcube, where we just put in a certain store ID, which is EOPF-Zarr. The most important operations of a data store are listed below. So you can list available data sources with the list data IDs method. Then you can check the availability of a certain data source with the method has data. Then you have the opportunity or the possibility to view the open parameters for each data source, because they vary from Sentinel product to Sentinel product. And lastly, the most important method is open data, which actually gives you access to the data, where you put in your data ID and your open parameters. There are further functionalities which are less of importance, but they can be viewed in our Python API. So regarding this data store, the Xcube EOPF data store, here are the main features. So in the end, it basically uses the xarray EOPF. Okay, I will continue with my local notebook because the kernel died on the Jupyter notebook. We stopped here. Okay, I start here again. So it uses the xarray EOPF backend to access the actual EOPF Zarr samples, and then it leverages xcube data processing capabilities to generate a 3D data analysis cube. And this is currently implemented for Sentinel-2. And the general workflow to build a 3D data cube can be summarized in 4 steps. The first one is that we query our products using the EOPF STAC API. So we propagate a time range and a spatial extent bounding box to our STAC API, and then we get the items, so the products within that spatial temporal extent. Then we retrieve and open these observations using that xarray EOPF backend, which was presented in webinar 3. Then we apply a certain mosaicing technique where we align multiple spatial tiles on the same day, which are adjacent. We will see that we will see an image later. And we do that per time step. And then we stack along the time axis to get our 3D data cube. A more in-depth description of these 4 steps you can find in the documentation. But now we would like to start and see that in action. So I import the modules which I need, which are basically Dask and xarray, and yeah, some functionalities from xcube and also xcube EOPF. This just helps that the cubes are rendered nicely by hiding the attributes here. This function is how you initiate a data store. So you use the new method, new data store, and we take our data ID EOPF-Zarr. And then we can run through the basics of a data store, the basic functionalities. So we can list our data IDs. We've implemented it so far for Sentinel-2. So level 1C and level 2A is available. Then you can check for the availability with has data, which returns your true because this is implemented. If you want to see if you can also reach Sentinel-1 GRD, this is false. At the moment, this will be implemented later. Then you can use this get open data parm schema, which gives you the opening parameters. And it gives you a JSON schema, and then you get it per data ID, so per Sentinel product, basically. And in there, you get all the different opening parameters which can be used, which I will explain you in a minute. But first, I will give you some background how the data is stored for Sentinel-2. So first of all, Sentinel-2 is a multispectral imager, and it has multiple spectral bands with different spatial resolutions. So we have certain bands on 10 meter, 20 meter, and 60 meter. Next, the Sentinel-2 products are organized in stack items, or at least in a catalog, and each stack item represents a single tile. A single tile, for instance, you see here, the green one. These tiles slightly overlap, and they are stored in the native UTM coordinate reference system. So they change from UTM zone to UTM zone. What the software specifically for Sentinel-2 does, the first step is exactly the original step. So we have a stack query, we use the STAC API, take our bounding box and our time range, and we get all the items within this extent. Then we sort the items according ordered by the Solar acquisition time and by the tile ID. So each tile gets a certain ID. And then for each UTM zone, we align these tiles into a greater data set. So adjacent tiles are basically placed next to each other, and no reprojection is happening here. So it's really the original pixels just placed into a larger data set. The overlaps are resolved by just taking the first non-nan value. Then the fourth step, it's the most complicated step. It's basically how to assemble the final data cube. And for this, there are 2 options. One is the native resolution preservation, and the other one is a reprojected or resampled cube. For the first scenario, this happens if you request a bounding box, which is within a single UTM zone. And you request that CRS of that UTM zone, and you request a spatial resolution which matches one of the native resolutions, so like 10, 20, or 60 meters. Then we only do an up or down sampling to align for the different resolutions of the spectral bands. And apart from that, we just crop that original data set to your bounding box, such that the original pixel value is actually preserved. In the second case, if you have, for instance, a very large data, you request a very large data set which covers multiple UTM zones, then, for instance, you would need to reproject at least one of the UTM data sets to actually align them together to one data cube. Another possibility would be if you request your data set in another CRS, for instance, SPSG 4326, which is in lat long, then we also need a reprojection happening on that data cube. Or you just request your data set in a complete different spatial resolution. This is also possible in the software. But then what happens is that with the CRS, the bounding box, and the spatial resolution, we build a target grid mapping, and then we just either resample or reproject onto that target grid mapping. Okay, that is the theory behind the cube generation. Now I would like to explain the opening parameters, and then we actually open the first data cube. So the same function, get open data param schema, can be also used with a parameter data ID, which I set to the L2A. And in here, you get your properties. And when you flip down here, this JSON schema, you actually get a title and a description and how your data ID can look like. So it could be a string or an array, for instance. I will not go through this entire schema because I summarized it here down in the text. So the required parameters is the bounding box, then the time range, the spatial resolution, and the CRS. This basically defines your target grid mapping and your spatial extent. Option parameters are variables. If this is not given, you just request all the spectral bands. And for L2A, also these the classification and qualification layers, which is cloud probability, snow probability, and scene classification layer. Then you can also select the tile size, which is the chunking, the spatial chunking of your final cube. You can add query parameters, which is propagated to the query request, because our stack catalog allows querying for specific properties, for instance. And then you can also select the spline order or the aggregation method, which I used doing the down and up sampling. However, I would recommend just keeping the default because these align with the Sentinel-2 specification by ESA, which is nearest neighbor for scene classification layer and cubic as a default. And then we have mean. If we go to a to a coarser resolution as an aggregation mode, it would be taking the mean over the superpixel or the center for the scene classification layer. As a note, when you use here open data with your opening parameters, it actually checks in the beginning if your opening parameter fit the schema, and if it doesn't fit, you immediately get an error that your opening parameters are wrong, and it tries to give you advice how to improve your opening parameters to get them correctly. Okay, with that, we can open the first data cube. So I select the bounding box, which is Hamburg area. I select the, I set the CRS to the native UTM zone, and I use the reproject bounding box method, which is an xcube EOPF, to actually reproject this bounding box. And then I can open up this data cube where I select data ID equals Sentinel, equals to the L2A of Sentinel-2. I take the bounding box in UTM. Spatial resolution should be 10 meters, and it should cover the first week of May this year. And I select just a few of the variables, which is band blue, green, and red, and the scene classification layer. As a note, this just builds up a DAS graph, so the xarray dataset is returned in a lazy way. to actually load the data and visualize it, you can use the usual plotting routines of xcube, and then you get a plot of the band 4 is the red band over the area of Hamburg. As a next step, I open exactly the same cube, but this time in another CRS. I use the geographic projection EPSG4326. As a note here, the bounding box is then in lat long, and I requested a spatial resolution where I converted from meter to degrees, approximately, and then of course the CRS I assigned to the geographic projection one, which gives me the same cube, but in a different projection. So we get more pixels along the longitude, and then we can also plot this result, which then gives me a plot in latitude and longitude. Okay, as a next step, I would like to open up the Sentinel-2 L1C product. For this, I just assigned a data ID to L1C. Apart from this, I just kept all the opening parameters as the first example, which gives me, except that I cannot request the scene classification layer because this is not available in L1C, which also works as expected. And also here we can plot the result. Okay, as a last step, I would like to show you a more complicated example, which is a more end-to-end example, which covers the data access, where we use this plugin which I've just presented. Then we save the final data cube and persist it, and then we use xcube to visualize it. So I have prepared this already because it takes a while to write this larger cube. And what I've done, I've selected a larger spatial extent which covers Mount Etna, and it should be a longer time period which spans the entire month of May. Since this job is a bit larger, I limit the task prioritization to 4 workers, which can be done with this line where you configure your scheduler in task to number of workers equals to 4. This ensures that everything runs more stable and reliable. So I have prepared that already, which gives us a data cube. So this is just an image, what you see from this script on the side. So you see a data cube with 15 timestamps with about 3,000 stamps, 3,000 pixels, and the build up takes about a minute. Then next I wrote this final data cube to our local file system. So this can be done here. We just use exactly the same function as before, new data store with the store ID file. This gives us an xcube data store, which links to the local file system. The root is set to data. So in data, I actually get my data cube, which I've written in here. And then I just wrote the final data cube, which I got from the request up here, into this file. As a note here, I used levels as a format, and levels is a multi-resolution Zarr format, which is specific in xcube. It is conceptually similar to a cloud-optimized GeoTIFF, but it's based on Zarr. So when you go into this data, you get multiple layers, where 0 is your base resolution of 20 meters, so the original resolution, and then each layer decreases the resolution by a factor of 2. So this helps, these different resolution level then helps when you zoom in the viewer app, such that everything loads nicely. Okay, so the next step is visualizing this cube. If we would be on a Jupyter Hub, we would also need to set this environment variable such that the URL is linked to your workspace. And then we can open up this data cube and we can see how many layers we have, which is 5. We can open up the level 0, which is our original resolution of 20 meters. And then we can use xcube viewer to actually visualize the cube. For this, I prepared a small config file where this part assigns you which data cubes you want to see. So you assign here a file data store with the root data, and your path is your file, well, the file name of your cube. And then we can also assign a certain style, which is defined here. Which is defined here. So you can define the color maps of your V2 and your scene classification layer. And for the scene classification layer, actually define as a very specific color map, which we will see in a minute in the viewer. So we basically load here this config file, and then we open up a viewer instance where we pass this config file. And with viewer info, you get your URL. And when you click on the URL, the viewer starts, and then you actually see our viewer. In here, so here, if you could select in the config file, you could select multiple data sets. This could be then selected over here. Here you see your data variables, which is your band TB2, which is the blue band, and the scene classification layer of your cube. You could, for instance, just change the color map within this user interface. What you also can do is you can pin this variable, and then you can select a second variable, and then you have the slider, and you actually can compare, for instance, if the cloud recognition in the scene classification worked nicely, you can just have a rough checkup on this. Then, yeah, for the scene classification layer, we get our predefined color map, which we have configured. And then you can also, let's go back to the spectral band. You can also get time series. For this, you need to select, for instance, a point, which gives you your time series. You can take a second point, and then you can compare these 2 points, for instance. So these are the different time steps, which you can also select here, these different images. You could also just take a circle or a polygon, and you can also make statistics with it, which basically calculates you the histogram within this circle. There are many more functions in this viewer, but I think these are the main one which I wanted to show you today. I would rather go on with this webinar. So there's also the possibility to take the viewer.show, which gives you an instance within the Jupyter notebook. This can be nice for a quick checkup. Of course, the web application is a bit more handy. And if you don't want to write a config file, you could just open up an empty viewer instance and add your data set, and then just show it, which also works fine. But then, of course, you don't have any configuration, so you would need to do it by hand in here. Yes, so this is all what I've prepared for today. So I would like to conclude. So today I demonstrated you the current development state of xcube EOPF Data Store and what you can do with this data store. So this data store basically adds a new data store to the xcube ecosystem with the store ID EOPF-Zarr. The main or the key points which I would like to take from this webinar is that we built this data store to build 3D analysis-ready spatiotemporal data cubes from multiple EOPF Sentinel Zarr samples. The general workflow, how these 3D data cubes are built, is first, we query via the EOPF STAC API to get all the stack items within a spatiotemporal extent. Then we read these data sets or the EOPF samples using the xarray EOPF backend. We do a mosaicing along the 2 spatial dimensions, and we do a stacking along the time dimensions. And then lastly, the general end-to-end workflow within the ecosystem of xcube would be to use the data access. For the data access, we use that newly implemented data store. Then we can write this data cube using file system-based data stores like file or S3 to persist that cube, and then we can use Xcube Viewer to visualize and explore this data. For the further plan of this project, or of the Xcube EOPF plugin, is that we're going to extend the support for Sentinel-1 and Sentinel-3. Again, I encourage you to use the software and give us feedback such that the software gets better and also develops according to user needs. And we have a continuous development until the end of the project, which is January 2026. And yeah, that is, I think, all for today. Thank you for your attendance. And I'm open for questions.
Thank you very much, Konstantin, for that presentation. Really nice to see these tools and these activities coming together, and very nice to build on what we learned in webinar 3 in a slightly more detailed way, accessing multiple Zarr files and using also the STAC catalog. Right now, I don't have any questions from the audience, so I would invite our participants to join us at slido.com, or you can scan the QR code. And if you have any questions, please type them in there, and we'd be very happy to answer. But maybe while we wait, just perhaps a silly question from my side as a non-specialist. Let's say you go through this process and you've developed your data cube, but you want to change what was in there, right? So is it possible to build these things programmatically? Can you dynamically spin up a data cube if you wish to access different data that then goes in there? Say you want to access a different time frame, or maybe your spatial extent changed.
Yeah, of course. With the bounding box and the time range, you can just select the time range you want to have and the spatial extent of that cube. So these are the 3 dimensions of the 3Ds: time, x and y, or lat and long. And with the opening parameters, you select which areas of the globe you would like to have.
But you have to rebuild the cube. It doesn't it's kind of like dynamically. Yeah. Okay.
Yeah.
Okay. Thank you. All right. So we have some questions now. Is the GUI code open source on GitHub?
The GUI code is probably the viewer. This is all open source. Entire Xcube ecosystem is open source.
Mm-hmm. And is it on our GitHub, or is it provided? Is it like a import?
It is spin up within our Jupyter hub.
Okay.
So Xcube is installed on a default image on our Jupyter hub of the EOPF project, and it then just works in there.
Okay, super. Thank you. Question from the viewer here: why do you suggest to use xcube and not only xarray?
I would say it depends what you would like to have. So if you want to just open up a single tile, use xarray with the EOPF Zarr backend. If you want to have something more sophisticated, like Sentinel Hub basically does, giving you a 3D data cube, then you need to use xcube EOPF. It builds on top of xarray.
Okay. Okay. How could send-to-core processor be implemented in the cube?
At the moment, not at all. However, the viewer or the server has the possibility to just implement any kind of function which takes an xarray dataset as an input and returns an xarray dataset as an output, and this is then calculated on the fly. So with a bit of coding and implementing a function, this could be done on any input you have in your cube, but not within this plugin itself. It's more like an xcube.
Okay. Thank you. Another question, how big or up to date is the database for Sentinel-2 data right now, and when will it be ready for productive use?
Yeah, so we started publishing coverage maps in this project. I think they're available by the STAC API. If I'm not mistaken, we will correct this if I'm mistaken. In general, at the moment, it's the last months, and it covers mainly Europe and I think also Northern America. But we will provide the link to the coverage maps.
Yep, definitely. Okay, thank you. Okay. How are you building up the overviews you used for the visualization? I hope the question is clear to you.
So if I understand it correctly, first of all, we use our plugin as data access. This gives me the task graph, so it shows me the data cube in a lazy way. Then I write the data to my file system. In there, the actual download happens and all the computations and, well, reprojection, if applied, are happening. And then I have my ready final data cube, which is used in the visualization. If I would not do this, the viewer would just be endlessly slow because then all these calculations would be done on the fly, which is technically possible, but not feasible.
Okie dokie. Thank you. Maybe one that was possibly asked before. How is the data in the Zarr store chunked?
For Sentinel-2 on a 10-meter resolution, a chunk is like 1,830. For the other resolution, I would need to look it up again. Yeah, we answered this.
We can publish the table.
We republish that on the answers list.
Okay. Is there an open source code to create the STAC catalog and Zarr metadata attributes from the raw binary data?
I'm not sure if this is public. Maybe Christoph knows it. If not, we will answer it later.
Okay, we can take an answer from Christoph. Christoph, we can't hear you yet.
The metadata is already included in the Zarr attributes, so you can read it directly from there of the Zarr Data Store. And open source for creating stack catalogs. Yeah, there are many libraries around to create like PyStack to create catalogs.
Okay. Thank you, Christoph. Okay, how do you deal with the building of data cubes for Sentinel-1 GRD products available on CDSE, as there is no terrain correction like Sentinel-1 RTC on Planetary Computer?
Yeah, we are still working on that. We do have our Snap developers in our team. So for Sentinel-1 in my team, our expertise is kind of low, so we will copy the expertise from the Snap development. For Sentinel-3, we already have everything in place, and this development should be quick. Yeah, I cannot say more on this, but once we find a solution, of course, I will write it further in the documentation how we built the data cube.
Okay. Thanks. Just to get a couple of easy ones, if you like, out of the way. So will the notebooks from this meeting be available on GitHub? And can I get the link of the GitHub repo? It was a second question.
Yes, the link to the notebook is already in the chat. This is the link to the notebook gallery, and from there you can also get to the GitHub.
And of course, all the resources used in the webinars are available also on the website for longevity after the webinar closes and so forth. Okay. Your previous answer suggested that xcube can make a cube of data, and that is the plus compared to xarray. But if the reader understood correctly, xarray can stack the time series as well. Thus, xarray can make a cube of data too.
If you only open up one tile ID, that is true. So in my code, in the back, I just use xarray concatenate to stack along the time axis, but then more is happening for actually mosaicing adjacent tiles in the spatial dimensions.
Okay, thank you. Can I create a stack catalog of the personally create cube using xcube, created cube, I suppose, yes.
Yes, xcube server has a STAC API and all the cubes which are published by the server are also published in a STAC catalog. I can present a result. So we take this question also, and I will provide a link to that.
Okay, thank you. When I create a cube, can I add additional products and have them indexed in the cube? Can I do this programmatically and store the new data in the cube?
Can add additional. Yeah, so the store open data method just gives you an xarray data set, and what you do with this xarray data set depends on you. So yeah, you can further modify it, add more other variables. That is definitely possible.
Okay. And yeah, last one for now. Sentinel-2 Zarr samples so far have been single images. Could xcube EOPF Data Store support time chunk size larger than 1 in the Zarrs, potentially useful for a locally assembled Zarr?
We discussed this in this project, but at the moment, this project is really only about mimicking the current archive, which are the tiles for Sentinel-2 as the JPEG 2000 tiles, and really just get a one-to-one representation of the archive in the Zarr format and show that this runs better. I guess this would be like one step further where multiple tiles are combined into a bigger Zarr. Technically, I would say Zarr is a perfect thing for that, but I would do it step by step.
Okay, thank you. Christoph, you have your hand up?
Bad.
Yeah, sorry to interrupt here, but I think the question was about xcube EOPF. So I think that's exactly what you have shown, right? That there are more than one timestamp.
Oh, okay. Now I understand. Yes. Yeah, you can take the time, well, you can extend the time range and then you get multiple timestamps. You get a 3D data cube, first dimension's time, the other two is your X and Y or lat and long. And then the chunk size. No, at the moment it's programmatically not possible. You could write an issue, then I could include it into the plugin. At the moment, you would get a data set with a chunking equals to 1. And then you would need to rechunk. But yeah, technically that would be possible to put that in the second cycle of development.
Okay, excellent. Thank you very much. Follow-up question from what you answered before. You said that the plus or the positive aspects of xcube compared to stacking time of xarray, you said there's more happening behind the scenes. Could you elaborate?
So you could request a larger bounding box, which includes multiple tiles, and xcube EOPF then first mosaics these tiles, which are lying next to each other, into one data set, and then it stacks along time. So it's not only a concatenation along the time axis, but it's also a concatenation along X and Y for multiple tiles.
Yeah. Okay, very good. Thank you. And another one here. Can the viewer of a newly created xcube be made publicly available?
Well, once you install xcube, you can use the viewer. It's an open source package, and the viewer is included in xcube, if that answers the question.
My reading would be that can that then be viewed by someone else who wishes to do so on the public internet?
Yes, we use the view in multiple projects where we have certain data cubes And then, of course, you need to host this web page. But then we publish that viewer or that viewer web application, and then user can use that web application to actually view the data. That is possible.
Great. Thank you. Thank you all of you for your questions. I think we'll draw the line there. Thank you very much for all of that. And thank you, Konstantin, for your insightful presentation, which generated a lot of follow-ups there. So I'd like to remind everyone that the recording of this webinar is going to be made available on the website. If you have any questions, please feel free to reach out. You can reach out via our support platform. I'd like to remind you of our upcoming events. So the 5th webinar of the series will take place on July the 8th. And you have the poster there. It's reusable deep learning with EOPF Zarr samples. And we will be present at the ESA Living Planet Symposium taking place next week. So you can scan the QR code here to find where exactly we'll be, the team will be working and presenting. So if you want to stay informed about our activities and upcoming webinars, please make sure to subscribe to our newsletter. You can do that on our website. And you should see a pop-up appear in front of you from Zoom. And we'd be very grateful if you'd provide us with your feedback about today's webinar. It helps us to improve and do better the next time around. So thanks all of you. Thanks, Konstantin and Christoph. And we hope to see you all again at future events. Have a great day.